Hello, hello, beautiful people, and welcome to 6-2 multiplying and dividing radical expressions. Multiplying and dividing radical expressions. So today our swab act, as you might have guessed, is going to be to multiply and divide radical expressions. So properties of radicals. The first one is the nth root, that's how we're saying this, the nth root of a times b is equal to the nth root of a times the nth root of b. Similarly, that's for the product property. For the quotient property, the nth root of a over b is equal to the nth root of a over the nth root of b. You've already kind of seen this before, except it was just the square root. And then just as somewhat of a flashback, square roots are like this, but what we don't say is the 2 on the inside, because it's just the square root. It's like the common one that no one really needs to differentiate for. So for our first example, we are going to simplify and assume that all variables are positive. So in the past when we've done this, it's been a square root and we were looking for perfect squares. This time we're looking for the fourth root. So I'm actually looking for perfect 4s, if that makes sense. And I'm looking at the 256, and I know that 256 is actually 4 times 4 times 4. And so this is 4 to the 4th. And then if I want a perfect fourth for the s to the 7th, it's s to the 4th times s cubed, because 4 plus 3 is 7. I'm trying to see how many perfect 4s can I pull out. Now, for the t to the 12th, how many perfect 4s? Well, I can do t to the 4th. That's 4. T to the next 4, that's 8. I'm trying to get as close as I can to 12. T to the 4th, that's 4, 8, 12. Great, which is what I was looking for. And then I'm going to pull out the perfect ones now. So how many perfect 4s? It's kind of like these cancel each other out, and then I pull it out. So now this is 4. How many perfect s's do I have? Well, this is 1, so I'm going to pull out an s. And then I have 1, 2, 3 perfect t to the 4th powers. So there's 1, 2, 3, so it's to the 3rd power. And then I'm going to put my leftovers in this root. So I took this out, I still have s to the 3rd in the radical. And then that is my answer. So perfect fourths is what we're looking for that one, because it was the 4th root. Okay, let's try another one just like the other one. And 4th roots, if you want, at any point in here, beautiful people, you can go ahead and press pause and try it, and then you can listen to me times 2 or times fast forward if you need to. 625, if you haven't already, go ahead and kind of start getting yourself familiar with perfect cubes and perfect 4s. In my head, 625, I think of 25 times 25, which is like 5 squared times 5 squared, 5 to the 4th. If not, you just look at 625, and you can make a factor tree. Old school, huh? 25 times 25, and get 5 times 5 times 5 times 5. 5 to the 4th. It's a delightful thing. Now I'm looking for perfect fourths. So it would be u to the 4th. But then how many would be left over? Just u. 4 plus 1, 5. I'm checking myself. And then y to the 4th is already a perfect 4th root. So this can come out as 5. I've got this one that can come out as u. And then I've got a y as well. And then my leftovers, 4th root of, well, the 5 is gone. Gone. I just have u to the 1st power, but I am not going to put that 1 up there. So 5uy times the 4th root of u. Perfect 4s is what we were looking for that one. All right, let's talk about the next phase in this. So that was just simplifying them. Now let's talk about, let's talk about multiply and simplify. Assume that all variables are positive. By doing that, when we take these out, we don't have to write, your book may, by the way, say that it's equal to the absolute value of that. They're telling us that it's positive, so you don't have to write the absolute value symbols for ours. Promise. Okay, so when I'm multiplying, I first like to think about this product property, and then I have separate ones, and I want to try to combine them into one radical instead. Because it's not so pointful to try to simplify here, and then combine them, and then have to keep simplifying a little bit more. So my first step instead is to combine them under 1. And I can do that because this is a cubed root and this is a cubed root as well. So what do we have? It's cubed root of I can multiply because it's the product. 9 times 12, and I would get a number that is 27 times 4, and that gives me, yeah, disregard that 27. 108, a negative times positive, that's a negative number. And then I have x squared times x, that's x cubed. We like that already because now I have a perfect cube. And then I have y to the 4th times y, which is y to the 5th. Okay, I'm looking for perfect cubes. Well, I knew this was 3 squared, just so you know. This is like 3 squared. And then this is 3 times 4. Right here, 3 squared times 3 is 27. And so that's me in my head, but otherwise, I'm looking at this 108, which you can kind of see in the calculator here, and I'm thinking, okay, well, what goes into 108? I know perfect cubes. I know 8 is a perfect cube, but it doesn't go in there. So I'm thinking, okay, what's that divided by 27? And I actually get 4. So this is 3 cubed times 4. And then I have my x cubed, and I have my, now I'm going to break this down. Break it down now. So this is y cubed. And if there was 5, I'll show you with my hands. If there were 5 y's, or y to the 5th, and I'm taking off 3, because this is my group of perfect cubes, then I have y squared left over. So y squared. And then I check myself. 3 plus 2 is 5. Check. So what am I taking out? Well, here's a perfect cube. 3. Here's a perfect cube. X. Here's a perfect cube. Y, because there's only one of them. And then left over, still in the radical, well, that's gone. I still have a 4. Gone, gone. And I still have y squared. Here's the thing that I just missed, though. This was a negative sign, and so this should really be negative 3 cubed. So I'm going to take this out as a negative. The reason why, this is like saying negative 27 times 4, and then this is negative 3 to the 3rd times 4, if you want to see more of a breakdown for that 108. Okay, so what did I do first for the last one? Same thing I'm going to do first now was combine. However, I'm looking at this 7 and this 2. They're both outside, so I'm going to multiply those and get 14. And then this is, there. If there's not a number, don't freak out, because this is what you first learned. This is just square root. Now I'm going to multiply what's on the inside. 3 times 6 is 18. I'm going to go in alphabetical order because I need to. X cubed, and then y cubed, because this is 2 plus 1 y cubed. Now, this time I'm looking for perfect squares, because this is a square root. Perfect square that goes into 18 is still 9, which is also known as 3 squared. I'm going to write it as 3 squared instead. What's 3 squared times 2? Okay, 9 times 2. And then perfect squares here. X squared times x. Y squared times y. What am I pulling out? Well, I had this 14 already. This cancels, so I just have times 3. This can come out. X, there's only one perfect y squared, so I'll pull that out. And then my leftovers are still in here. So I still have a 2, I have an x, and I have a y. The last thing I will require you to do is to multiply 14 times 3 and get 42xy times the square root of 2xy. And that is all we can do for that problem. Like it? Love it? I'm going to pretend like you said yes. Okay, now division. Same thing. I want to simplify first, though. I want to make just one radical if I can. So I have a cubed root, and this 4 is just 4. Now, what's x squared divided by x? X squared divided by x. Well, x goes into x squared one time because we can subtract the exponents. I don't need to write the 1 there. And then I'm going to look for perfect cubes. I don't see any, so that's it. 4 is a perfect square, which is great, but we don't care. We want perfect cubes for this one because it's the cubed root. Okay, same first step. Simplify first. This is a square root. 2 and 54. 2 goes into 54 27 times. X to the 5th divided by x squared. Remember, when you're dividing, you subtract the exponents. So 5 minus 2 gives me x cubed. and then y cubed divided by y to the first power, so subtract 1 and I get y squared. I love it. Now I'm looking for perfect squares. So 27 is 9 times 3, 9 being my perfect square, so I'm going to write it as 3 squared times 3, x squared times x. Y squared is already a perfect square, which we kind of like. Okay, perfect ones come out. There's one perfect square for 3, so I'm pulling that out. There's a perfect square for x, there's a perfect square here, and a y. What's left? 3 and x. Beautiful. If at any point you need to, you can always press pause. You can also replay an example if you feel like it went too fast. You can do ×2 if I'm going too slow for you. Okay, rationalize the denominator. So remember, the same thing with square roots is that we cannot have any radicals in the denominator. It's just not allowed, so we're going to rationalize it. And we're still going to be assuming that all of my variables are positive. So, first things first for me, I do want to try to simplify as much as I can before I do anything else. Do I? Yeah, I kind of do. So I have the cubed root. I'm going to make this under 1 cubed root. 7 and 4, no I'm not. I can't reduce that, so I'm going to leave it. But these x's I can. I have 1 x on top and I have 2 on the bottom. So I can technically take off 1 x from both of them. And where do I have an x left? Right here on the bottom. So like this x is gone and this 2 becomes 1. It's a different way to simplify. Remember, if you had 2 on top, so this is what it looks like. I had x over x squared. And then what I'm doing, x over x squared, is just canceling and canceling. That's why I'm subtracting 1 from each one of them. And I have just an x on the bottom. So the numerator, golden. Nothing I can do, and actually nothing that I want to do. The denominator, though, got a little bit of a mess. So before, I would have just multiplied, square root of 4. Square root of x. But that doesn't work because I'm not dealing with square roots. So for this one, beautiful people, I'm not looking for perfect squares. I'm looking for perfect cubes. But here's how I'm going to get there. This 4 is like 2 squared, and then the x. Yes? Yes. So in order to get rid of it, I'm going to multiply the top and the bottom by what? Well, my goal is to get those cubes to cancel out. So if I have 2 squared on the bottom, to get it to cancel out, I need it to be 2 cubed. Then those will go away and I'll be a happy camper. Well, if I have 2 right now, I need to multiply it by 1 more 2, because 2 squared times 2 is 2 cubed. Now the x's, I have 1x. I need it to be x cubed in order for it to cancel out. So I'm going to multiply. If I have an x here, I need 2 more in order for it to cancel. Now whatever I do to the denominator, I must also do to the numerator. 2x squared. So let's see what this looks like and see if my goals have been accomplished. I have the cubed root of 7 times 2 is 14. Y squared times x squared is just x squared, y squared, over, now this was 2 squared times 2. That's 2 to the third. This is a cubed root still. And then x times x squared is x cubed. Beautiful. I needed perfect cubes in the denominator, and I got them. So the numerator stays the same. 14 x squared, y squared. The denominator, now, perfect cubes. This is a perfect cubed, so it's just 2. Perfect cube, just x. I have rationalized the denominator now because I don't have any more radicals there. I will not have time to go over this example in the bottom 2, so I'm going to stop this video right now, and we'll start right here in the next video. Thank you so much.